Hi everyone, my name is Michelle Barboure and I'll be presenting to you my master's internship project on predicting autism from EEG using machine learning. Autism spectrum disorder, ASD for short, encompasses many different phenotypes and may affect communication, movement and social abilities. However, currently, ASD is diagnosed based solely on behavioural observations, leaving room for subjectivity and misdiagnosis when it comes to such a complex and diverse disorder. But recently, studies have started using brain imaging, such as fMRI and EEG, together with machine learning to predict ASD, with the goal to assist the current diagnostic procedures, making them more objective and robust. So with all this progress, where's the gap in current research for my project? Most studies that predict ASD using EEG and machine learning have, for one, focused their efforts almost exclusively on children, two, have focused on resting state EEG recordings, and three, have used an oversimplified ASD or non-ASD binary classification approach in their model design, which leads to problems with the very definition of ASD, and that is that it lies on the spectrum. So, what about research in adults and using EEG data from task-based recordings and trying to implement a more ASD spectrum conscious model? And this is where my project fits in. So the goal of my project was to determine whether we could use EEG from visual tasks in adults to successfully classify ASD by implementing a spectrum-orientated model design. You may be wondering at this point, what is this spectrum-orientated model I keep on talking about? Be patient with me, I'll explain it in a bit. So first, let me briefly run you through the study design itself. The study cohort consisted of 84 participants between the ages of 18 and 55 years, equally split between ASD and controls. Each participant was asked to perform two visual tasks, the boundary detection and the orientation discrimination task, BD and OD for short. It's not particularly relevant to this project how exactly they were performed, but just know that it involved the participant to look at the screen as the images changed slightly, and they had to make decisions of whether to click left or right. We collected a bunch of information about the participants too, of which two acted as target features for training the machine learning models. One was obviously the ASD status, whether they had ASD or not, and the second was the Autism Quotient-Short score, which was obtained through a brief questionnaire. So what is the spectrum conscious model I keep on referring to? So remember I just mentioned that two features were used for the machine learning models. One was the ASD status, so a binary on and off switch, and the other was the Autism Quotient score. Now, if we combine these two features together, we notice something interesting. If we use the recommended cutoff of an AQ score of 65, the AQ score alone is actually able to distinguish between ASD and non-ASD participants very well. The added advantage here is that the AQ score is more of a continuous variable. We see here values between 40 and 100. And it is now possible for a model to differentiate between a mild case of ASD and an extreme case of one. Let me try explain the advantages of this a bit further with this visual. By using the AQ score as a target variable, it also gives us more room for optimization. We can now change the cutoff to see what actually divides the group best. And the model also receives more of a detailed feedback of how wrong it was. Instead of getting feedback of you're wrong, it now gets feedback of you're wrong by 15 AQ scores. The methodology of this project can be divided into the brain imaging preprocessing step and the machine learning step. Very briefly, I used the open source Python library MNE to clean the EEG data. I then performed signal averaging, feature engineering, and feature selection on the data. This data was then split into a train set and a test set. I chose 5 different learning algorithms, and where each algorithm was implemented as a classifier, so this on and off switch approach, or a regressor, which is using this autism spectrum score, depending on which approach I had used. I then used different performance measurements to evaluate these models. Now the question remains, what combination of variables actually gives us the best predictor of ASD? Is it this on-off classification approach, or rather this continuous AQ score regression learning approach? What task gives us a better prediction? Is it the BD task or the OD task? And what are the best combination of features? Is it using 10 features that gives us the best score, or 140, or anything in between? And what is the best machine learning algorithm out of the 5 that I had chosen? To try to answer this question, I used an extensive grid search approach where you essentially combine everything with everything else and see what best combination works. And this is what the result is. So I know these graphs are quite intense, but each graph shows the prediction accuracy on the y-axis across each algorithm. So that's each line, different colored line that you see. And this was done across the regression approach and the classification approach, as well as across the BD and OD visual tasks. So those make up the 4 different headings that you see. And on the x-axis, you see that this is done across as the number of features varied. So that's between 1 feature and about 150. So over all combinations, the decision tree algorithm was able to predict ASD best with an accuracy of 83% using the boundary detection task, this regression AQ score continuous variable approach, and using 12 features. Therefore, the best configuration was using the boundary detection task, using the regression learning type. Done. Not so quick. So we know that accuracy is actually not always the most reliable indicator for a model's performance. So I looked a bit further into it, and I took the best combination of features for each model and plotted a receiver operating characteristic curve for each of them, which is what you see here. This type of graph allows us to see the performance of a model across all thresholds. So that's using this autism AQ score approach, but then having this changing cutoff. So it was 65 initially, but that can be adjusted. And a model with the highest AUC, which is the area under the curve, is able to distinguish between ASD and control subjects best. And as we see here, the random forest algorithms actually outperforms the decision tree, making it overall the best at distinguishing ASD from controls. So, in conclusion, the results provide evidence that machine learning algorithms can distinguish signatures from EEG data of adults performing visual tasks. And secondly, a classification model using this AQ score, short score approach as a target feature resulted in the best predictive models, providing a novel approach on how to implement machine learning to detect ASD. Overall, this shows promise for future applications of machine learning in the assistance of ASD diagnosis. And with that, I've reached the end of my presentation, and I thank you very much for your time and attention.